Hello and welcome to CUDA Weekly. I'm your host Johan Bontes and today is episode 007. So what would be more appropriate than to talk about locks? CUDA has integrated a whole bunch of synchronization gadgets from the standard C++ library, and they would have you believe that using them is as simple as porting your code from the CPU to the GPU and just following the documentation of the C++ library. Is it really that easy? Let's have a look. Let's have a look mutexes in CUDA. Now CUDA has a number of items that they've copied or implemented from the standard library, and among those is a whole bunch of synchronization items. Atomic, obviously, a latch, a barrier, and what is called a counting semaphore. And if we just count to 1, then well, that reduces to a mutex. They've helpfully included examples, which are not very helpful because that doesn't actually tell you anything about how to use it. If you want to get the examples, just go to the examples for the standard library. But unfortunately, those do not apply when you look at CUDA code. Let's have an example of how this stuff is actually supposed to work. We're back in Compiler Explorer. Let's implement the mutex. Okay, that was a lot of code. Let's work our way through it. So in order to use these semaphores, we have to include the header. Then we create a global, in this case, to keep it simple, mutex header. A binary semaphore is basically a mutex with a scope of device. So that means that it works across the GPU. We initialize this thing with a 1, meaning that it is available. If you don't do that, bad things will happen, as I'll show you later. Next, we add a little helper to create and destroy locks so that we get, a lock within a scope, make things easier. Then we have a constructor which acquires the mutex in a single thread, very important. If you try and acquire it in multiple threads, you're going to have a deadlock. Then we synchronize as, the struct says on the tin, it needs to synchronize, so that's what we do. The destructor, no surprises there, releases it once, not more than once, otherwise, again, that's not going to end well. And then we synchronize again, as promised in the name. Next we have a structure, very complex structure with lots of internal details. In this case it's a simple array. We need to initialize that one because it's a global structure for the example here, and we can't put a constructor on a global. So we have a separate init that initializes the data. Then we can add items to our complicated data structure. We first have a shared int to track the increase. This is so all the threads inside a block can see the same value. Then we log within this little scope here. Now why did we put that scope? When we return old count, we want to do a sync threads. By enclosing this mutex within that scope, it's going to get destroyed here. That calls a sync threads, which means that we don't need to do another sync threads. If we were to do this, everything would still work, but the sync threads would happen after old count, which is not what we want. So by simply putting a scope around, we don't have to do an extra sync threads. So we log here, right? It will go out of scope at the end, so that's fine, it will release there. And then we get our count using an atomic add. Then we add our data into our structure. There's only one thread here, and all the other threads, all the other blocks are locked out, so that's perfectly safe. And then we return the count before the add, so that's actually the index where we've added our item. Okay, next we want to get data. Now, if we get data, we do not want data to change from underneath us. So again, we log as before, using the same scope trick as before. So now we have a shared int result. We put our data into result using a single thread because it makes no sense having all of these threads hammering results. It's more efficient just to do it in one. We could code it up like this, which is probably a tiny little bit more efficient. And then we return the result. That's safe because there is a sync threads happening when the log goes out of scope. The cache is a global. Now we have two kernels. One that initializes the cache and one which actually does stuff. So when we call here init cache and then we call do stuff, in between these two get synchronized. So first init cache runs and completes, and then do stuff runs. This is the case because we only have one stream, the default stream, and if you run thing in a single stream, these things get synchronized, which is exactly what we want. Okay, so first initialization, and next we get to doing things. In this case, we run this thing for, well, 100 runs, and we add items to it, get items out of it, and print some interesting stats. Let's have a look at the stats. So here you can see blocks get added, and these things are nice, kept out of each other's way. Also, very important, you did not see any deadlocks. Now let's have a look at what happens when we change a few things in the code. Here we've actually not initialized the mutex, we just leave it as standard. That means that it's gonna have a 0 within it. If we then run it, you can see that it deadlocks. The init gets to be done, but the program gets to be utterly stuck. In fact, the thing gets killed because we've exceeded the time that Compiler Explorer allots to us. Rule number 1, we need to make sure that our mutex starts with a count of 1. If we log not in a single thread, then surprise, surprise, we get another deadlock. We didn't ask for the mutex to be acquired in a single thread. That obviously is going to get a deadlock. If we release the mutex multiple times, we're not going to get deadlocks, but we're going to mess up with other people's log of this particular mutex. If we disable this code, it's going to be really hard to show. If we disable this code, this log is going to get released about 1,000 times, and that's going to mess up with other people logging off the thing. Now we won't be able to show the effects on this really simple data structure, but take my word for it, bad things will happen. Okay, that's all I have for this particular CUDA Weekly. Let's maybe go over it one more time. So first thing we need to do is to get a binary semaphore with a scope that makes sense, in this case the whole device. Then you really need this thing here, so that you never have to worry about calling acquire without calling release. See? Because as soon as the scope ends, your lock will automatically get released. Then you need to have some really complicated data structure. I'll leave that as an exercise. You can initialize that thing however you like. Here I've used a separate kernel. Well, that's a decent solution. And then you have stuff that actually works. So within your really complicated data structure, start a scope when you need to actually lock the thing, and release that scope as soon as you no longer need your data to be locked. It's important to have the lock live as short as possible, because all that while that your lock is fixed on your cache, no other block in your GPU can actually access that resource. So you want this time to be short. And because the lock needs to synchronize the threads, you might as well take advantage of that. That's all I wanted to say for today. Thank you for watching. I hope you enjoyed the show, and I'll see you next week.